Let me talk about black holes for a little bit. The idea of black holes came about in surprisingly long ago, actually. In 1783, an English rector named John Mitchell came up with this idea of dark stars. John Mitchell was taking ideas that were relatively recent for his world, which were Newton's idea of gravity and how gravity works, and then Newton's other idea, which is that light consists of particles that have mass. And if you combine the two concepts, it's natural to come up with this idea of what he called a dark star. So something that was massive enough that could trap light particles so that they could never escape. His idea actually quickly fell out of favor once physicists realized that light, in fact, doesn't have mass, and they began to think that light was actually more of a wave than a particle. Turns out light is both a wave and a particle, but in terms of dark stars, if there's no mass to light, there's no way to trap them. So the idea of dark stars got dropped for several centuries, and it wasn't until 1915, when Einstein's equations were published, and Karl Schwarzschild was looking at them and actually managed to solve them, that the idea of black holes came about again. Let me first tell you about the general theory of relativity. This embedding diagram basically shows a two-dimensional analog for how general relativity works. Rather than having gravity work as this spooky action at a distance force, what Einstein was proposing was that any massive object bends the fabric of space-time around it. And so this is basically analogous to taking a trampoline and putting a bowling ball on it, and then you roll a marble across that trampoline. The marble is just going to roll in an orbit around the bowling ball. And so that's a two-dimensional analogy. It's sometimes a little bit hard to look at these diagrams and really see how they apply to the real world because we live in 3 dimensions. But it does give us a way of understanding how general relativity works. So now let's say we take that black hole and we make it more massive and keep pulling it down. That's going to eventually pull the curvature of space-time so that it becomes infinite. And at that point, you reach a point where you create an event horizon, this point of no return where light cannot escape. And so this is what Karl Schwarzschild wrote to Einstein in 1915 and wrote to him this idea of an event horizon and this idea that inside the event horizon, the curvature of space-time could become infinite. Now, physicists don't like infinity. Normally, when you're solving equations in math that have to do with physics and you come across an infinity symbol, it means you've done something wrong. But in this case, they kept looking at this idea of black holes, and what they found is actually they don't appear to have done anything wrong. They weren't able to find any way to get around this. Black holes must be able to exist in the universe somewhere. And I'll point out another thing while I'm on this diagram, is that black holes don't suck. And that's not just because they're my favorite mysterious objects in the universe. Because black holes they're just another massive object, and they're just another thing that's bending the fabric of space-time. So if you were to replace the sun in the solar system with a black hole of the same mass, the Earth would just continue in orbit around it, not noticing anything different except for the lack of light. How do we go about finding black holes? Well, the first black hole was actually discovered in 1963, but nobody actually had any idea what this object was. This object was 3C273, which is this object here, and it was actually a whole field of stars taken from a telescope at the Kitt Peak Observatory. And so all of these other objects here are just stars, and they're actually point sources, so the fact that you see them at a certain width, that's just telling you actually how bright the star is. But so this star in the center here is actually quite bright and has this wispy, weird thing coming from it. In the visible light, it actually looks just like a star. It's just a point source. But when they looked at this object in other wavelengths, they found that, well, first of all, it's emitting radio waves, much more than you would expect from a star. And you can also take the spectrum and look at the spectral lines from this object, and those spectral lines were really strange. Until one day, Martin Schmidt was looking at the spectrum of the star, and what he realized is, no, this isn't strange at all. This is actually just hydrogen lines. And we're seeing these hydrogen lines redshifted, shifted to the red end of the spectrum, by the fact that this black hole is moving extremely quickly away from us. So what he realized, and what he published in Nature in 1963, was that this can't be a star that's being ejected from our galaxy, because there's really no known mechanism that would eject a star at these kind of speeds. So what he wrote was the explanation in terms of an extragalactic origin seems most direct and least objectionable. So in other words, rather than being a star in our own galaxy, this object, whatever it was actually going by the redshift that they calculated and the expansion of the universe, would have to lie about 4.5 billion light years away. So the reason that was so astounding to astronomers at the time was that if it's that far away, this is awfully bright. So what can produce a power source that is that bright? So they considered a lot of different options, and what they ultimately came down to is that there was no other option than to have a supermassive black hole at the center of this galaxy. Now, when you first think about that, it doesn't make any sense, because black holes are black, you don't see any light. But it turns out when black holes feed, they actually produce a great deal of light. And so when gas flows into a supermassive black hole, it actually heats up. There's friction between the gas layers, and that heats up the gas, in the case of supermassive black holes, to tens of thousands of degrees. And you end up being able to see these objects as if they were stars, because they were so far away, in the visible and ultraviolet light. But their spectrum and everything about them is going to be completely different from a star. And so this is a simulation that shows you a little bit about how this works. Out here you see dust and then gas as it's flowing into the black hole. And as it's spiraling in, it gets hotter and hotter, so from red to white. And then what you're seeing here is some variability, some instability in the accretion disk. And then that causes some gas to flow along these magnetic field lines and down these extremely long jets. And so when you look at the object 3C273, and this is a more updated image from Hubble, you can actually see this long jet. This is extending out to 100,000 light years away from the black hole and very far outside of this galaxy. The other thing you can actually do with this image is subtract the point source in the middle, because most of what you're seeing here is actually the quasar. The quasar is outshining the galaxy, in this case, by about 50 to 1. And if you subtract that point source, you can actually see this quasar is lying in a giant elliptical galaxy. So it's really astounding that this small area that's about the size of our solar system is able to outshine an entire giant elliptical galaxy worth of stars. Now, quasars weren't actually accepted to be black holes for a little while. It took a while for astronomers to wrap their brains around that. But stellar mass black holes within our own galaxy were actually considered the better candidates for black holes for some time. And they were actually discovered at around the same time. So 3C273 was discovered in 1963. Cygnus X1 was discovered in 1964. So the 1960s were truly a revolutionary era in astronomy for a lot of different reasons, but this is one of them. What they found when they looked at Cygnus X1 is that you actually just see, if you're looking in the visible or ultraviolet light, you see this blue supergiant variable star. And if you look in the X-rays, you see that this supergiant star is orbiting a companion that we can't see. And that companion is an extremely powerful X-ray source. And so when you look at this system, there's really no way to explain it other than by looking at the orbit, you can see that whatever this object is, it has the mass of 15 suns, and it's emitting extremely powerful X-rays, so there's really no other explanation than for it to be a black hole. And so for decades, this was actually considered the best black hole candidate. And the reason that we're actually seeing this in X-rays rather than in visible and ultraviolet light is, in the case of stellar mass black holes, the smaller mass means that the gas gets closer into the black hole. And so it's actually able to heat up even hotter to millions of degrees and emit X-rays rather than the visible and ultraviolet light we see from quasars. So we can see quasars, and we can see stellar mass black holes when they feed on tremendous amounts of gas and they become these brilliant sources of light. But how do we find all the other mild-mannered black holes in the universe that aren't feeding voraciously and don't have this full dinner buffet in front of them? Well, astronomers have done a lot of different studies. One way is to look at the motions in the center of a galaxy, looking at the motions of the stars, and then you can tell that there's a black hole there, even if it's not accreting heavily. The conclusion that astronomers have actually come to is that every large galaxy in the universe actually has, or almost every large galaxy in the universe, has a supermassive black hole sitting at its center. So when you look at something like this Hubble view of galaxies, this is the Hubble Deep Field, most of the galaxies that you see in this picture have a supermassive black hole sitting at their centers. So black holes are actually extremely common. They seem to be just about everywhere. And what's really neat is you can actually look at this image in the X-rays. And if you look in the X-rays, every point that you're seeing here that's flickering, is actually a black hole that's feeding. And in these cases, these aren't quasars. These are actually just what we call low luminosity active galactic nuclei. So they're feeding on some gas, but it's really more just snacking. They don't have this voracious feeding habits. So what about our own galaxy? Is our galaxy a quasar? Well, no. We can say pretty definitively it's not, because we would see it in the night sky if it were. It would be a brilliant object. But it's possible that our galaxy would have its own black hole, and that black hole could be feeding. But for a long time, it was really difficult to tell that, because when you look at the center of the galaxy, it's of course covered by these massive dust lanes that lie within the spiral arms. So instead, we look using infrared, X-ray, and radio waves. And that allows us to peer through the dust and actually see through to all of the bustling activity that's happening in our galaxy's downtown area. And so what I'm showing here is a picture that shows this galaxy downtown. And the red here is the infrared from Spitzer and Hubble. And the blue here and here, all of that comes from the X-rays that were observed with the Chandra X-ray telescope. And basically what you're seeing here is a lot of star formation, a lot of star death. You're seeing supernova explosions. But you're not seeing a whole lot of activity from the black hole. The black hole turns out to lie right here. And this is the center of our galaxy. And we can see that the whole galaxy is rotating around this point. It is actually pretty bright in this image. It is emitting X-rays, and it is emitting infrared, and it does emit radio waves as well. But it's not as bright as we would expect. And it turns out the black hole, assuming that that's what it is, at the center of our galaxy is unusually docile. It's not really feeding a whole lot on its environment. So how do we even know that our galaxy has a supermassive black hole? Well, we can actually watch the stars complete orbits around the black hole, especially this white star here completes a full orbit around the black hole. And this video is truly astounding, because this is actually a collection of 16 years worth of observations. And they're looking at the galaxy's center in infrared emission, which allows them to peer through the dust. And they're also using adaptive optics, because that's the only way that you're going to be able to resolve stars that are so far away, because the galactic center is 27,000 light years away from us. What astronomers can do by watching these stars for 16 years and collecting them into this video, they're able to watch the star in the center complete a full orbit. And what that allows them to do is use just basic Newtonian mechanics and say, how much mass exists inside this orbit? Well, it turns out that that orbit contains 4.3 million suns worth of mass. So there's no way that we're going to be able to fit a stellar cluster in that small of a space, nor would it fit there without us seeing it, obviously. So really, the only explanation for what exists at the center of our galaxy is that it has to be a black hole. And so I actually consider this now to be the best evidence that black holes exist. So at this point, I just want to take a step back, because I often get questions, both from children and adults, about whether a black hole will ever pull us in. And I always correct them if they say suck. So black holes will never suck us in. But it's possible that they could pull us in. But if you're looking at the black hole at the center of the galaxy, even though there's 4 million solar masses in that black hole, it actually doesn't have a huge gravitational sphere of influence. It actually only extends out to about 10 light years away, which is pretty big, considering. But since we're 27,000 light years away, we don't have any worries. Unless our orbit gets drastically altered and goes into the galactic center, we don't have to worry about ever approaching the supermassive black hole at the center of the galaxy. Well, okay, so maybe not the supermassive black hole, but what about all these stellar mass black holes? I mean, of course, we see the ones that shine brilliantly in the X-rays when they're feeding from their binary companion, but it's perfectly possible that you could have a stellar mass black hole that simply reached a star that's reached the end of its lifetime and collapsed into a black hole, but doesn't have a companion to feed off of. And these stellar mass black holes probably exist in the millions in our galaxy, and we would never know about them. Except that it actually turns out that we would, because there is the interstellar medium, which is the gas that lies between the stars in the galaxy. And this interstellar medium is what the black hole would feed on, but it would be an extremely, extremely low accretion rate. But we'd still be able to see it if it came within about 100 light years of Earth, just using the current X-ray telescopes that we have, assuming that they're pointed in the right direction. We actually do have an all-sky X-ray monitor that's still working, that's on the International Space Station, but that's actually due to be taken out of service in September. So after that, maybe we'll worry a little bit more about it, but I wouldn't stay up too late at night worrying. So okay, we're not going to be pulled into a supermassive black hole, but let's just say for fun that we could send an astronaut over to a black hole and see what happens. Let's be nice to our astronaut. We'll call him Tim. We're going to send him to a supermassive black hole that has the mass of 10 billion suns. If we send him to a stellar mass black holes, he's just going to get torn apart quickly, and that's going to be the end. So we'll be nice to him. We'll send him to one of the most massive black holes that we know about. And what he's actually going to do is he's going to fly right through that event horizon and not notice a thing. He's going to pass the point of no return without ever noticing. He's going to free fall into the singularity for 20 hours without noticing anything. And it's actually only in the final second before he reaches the singularity that he starts to feel what quickly becomes an extreme stretch. It's actually a tidal pull, which is the same kind of concept of gravity of how the moon governs the tides on Earth, which is that his feet feel a slightly stronger pull than his head. And so he's going to start to stretch a little bit. And he'll feel it gently at first, but pretty darn quickly he's going to be stretched out as thin as spaghetti. And that's going to be the end of his experience. And he's not going to be too happy about that. So the technical term for that actually is spaghettification, and that will be the end of Tim's experience of the black hole. But is spaghettification actually the end of what happens in a black hole? And it turns out the answer to that is no. When Timmy starts to stretch out into spaghetti form, he starts to, at first it's just, he gets a little bit taller, but pretty soon he's stretching out close to infinitely thin and infinitely long. Well, when you stretch something out like that, that actually does crazy things to space-time. And so the tidal stretch that's producing curvature actually begets its own curvature. So it's gravity begetting gravity. And so that actually starts reversing the stretch. So you're stretching out in one direction, that the extreme tidal pulls there reverse the stretch, and you start stretching out the other way, and then you start stretching out another way. And so eventually this was dubbed the mixmaster effect, for the effect of kneading dough in a mixmaster. But so that's basically what Tim will be experiencing long past the point of being conscious of anything. All the matter in his body is actually going to be doing different things simultaneously. So his head might be stretching out one way, while his hand is stretching out another way, and it's going to be a completely chaotic mixing of all the atoms in his body. And then just at the moment when everything becomes infinite, when I say everything, I mean the oscillation of the stretching and the reversing stretching, and also the stretching itself, him stretching out into infinity. When everything becomes infinite, that's when space-time ceases to exist. That's when he enters the singularity. And Tim ceases to exist at all as matter and becomes simply part of the gravitational field of the black hole. So I often get asked, is there a way to travel through a black hole into another dimension or another universe? And there is, theoretically, there is a way that you can get the math to work out such that the curvature of the black hole eventually opens up, for lack of a better term, into a white hole. And that white hole could be in our universe or it could be in another universe. But the problem with wormholes, these wormholes that connect the two, are that they are extremely unstable. So if you throw any amount of matter into a wormhole, it actually collapses. And so the only way to stabilize a wormhole for your science fiction book is to throw exotic matter in there that has negative energy density. I have no idea what that looks like because we don't experience that in our ordinary life, but that's what you would need to get a wormhole to stay stable. And even when you do that, as soon as you throw any amount of ordinary matter in, it's still going to collapse. So unfortunately for Timmy, he's not going anywhere. He's just going to stay right in that singularity. So I want to talk now about, we're actually in the process of watching a little object named G2 as it approaches the supermassive black hole at our galaxy center. And this is an extremely exciting event because this object was first discovered in 2011. And what they thought when they were seeing it was that this was perhaps a gas cloud. And it seems to be headed on a straight course for the black hole at the center of the Milky Way. And so they kept watching this and kept watching this. And they're actually starting to see this object start to be stretched out a little bit. And it actually turns out that this talk has very good timing because right now this object, G2, is at its closest approach to the black hole, and we can see that it's stretching out a little bit. But it turns out we actually still don't know what this object is. So originally they were thinking this is a gas cloud, and in that case, this simulation that shows how the gas cloud approaches the black hole and gets torn apart, all of this would be accurate if this is in fact about 3 Earth masses worth of gas. And so you see the cloud approaching the black hole and whip right around it, but you'll notice that it doesn't start feeding the black hole right away. Most of it actually goes right past the black hole and then starts to spiral in and start to feed the black hole. And so even though this G2 is making its closest approach now, we're actually still going to keep watching the center of the galaxy to see if anything happens. As of now, and I asked an astronomer about this last week, we're not seeing anything unusual, any unusual activity from the galaxy center, but stay tuned. For the rest of the year, they're going to keep watching this and see what happens to this object. And the reason this is actually kind of controversial in the astronomical community is because this idea that it's a gas cloud could actually be entirely wrong. When you actually look at images rather than the simulation, you just see a little red fuzz. And so that little red fuzz could be a gas cloud, or another team of astronomers has suggested that it's actually a star that's enshrouded in gas. And so if that star makes a close approach to the black hole, that star has enough mass to hold itself together, and it's not going to be torn apart like the simulation that you just saw. It could be that the gas that's enshrouding the star would still would be stretched a little bit, and that might actually be what we're seeing currently. But even if that gas feeds the black hole, it's not going to be that much, and it's not going to perform a lot of activity. So it's really kind of suspenseful to see what's going to happen here. Is this black hole going to feed and have this, it could even create an accretion disk around the black hole, and we could see the jets being emitted, or nothing at all could happen. So we're either going to, later this year, see a feeding black hole in action, or we're not going to see anything at all. So we'll just have to wait and see. But whether or not G2 is a gas cloud or a star, there's actually a project going on to look at the black hole at the center of the Milky Way. And we can still watch it feeding, even just on its, just the ordinary, the gas that's in its environment. And we, of course, still can't see the black hole itself, but it's possible, if we have high enough resolution, that we could resolve the silhouette of the black hole against this background of ionized gas. And this is an extremely technically difficult problem because Sag star's event horizon is about 0.1 astronomical units, or 0.1 times the distance from the Earth to the Sun. And so that's actually within Mercury's orbit, to help you visualize that. And we're seeing this object from 27,000 light years away. So this is actually the largest event horizon that we could possibly observe, and so that's why we're going to target it. But the event horizon is only 20 micro arcseconds wide in the night sky, so that's not something that any infrared visible X-ray telescope is capable of doing. Now, strong gravitational lensing, the strong gravity field of the black hole, helps us out a little bit because that actually makes objects appear larger than they actually are, so by about a factor of 5. So this event horizon actually is going to appear to be 100 microarcseconds wide, but that's still really, really hard. So what astronomers are doing is they've taken on this massive project to put together an Earth-sized telescope, an Earth-sized radio interferometer. The way radio interferometry works is if you have a radio dish over here and a radio dish over here, and then you combine the signals collected from those two radio dishes, that's the same thing as having one large radio dish that has the diameter of the distance between the two radio dishes. So by collecting stations, radio telescopes around the globe, and combining those signals, you're actually creating a telescope that is the size of the Earth. And so far they have only a couple of these stations online, but they're working on adding more. ALMA just went online in Chile. They're working on adding that to the system as well. That's going to help a lot. And there's several other, such as the South Pole Telescope, they're also planning to add. So this is an enormous undertaking, still very much in progress. But what they've done so far is they've already published some first results. This is a technique called very long baseline interferometry. So 3 of these VLBI stations took a look at Sag star already, and they've published these results in 2007. And what they found is they weren't able to image the black hole because 3 stations isn't enough for that, but they were able to collect some data. And what they found is that this black hole appears to be between 27 and 53 microarcseconds wide. So if you were paying attention to 2 slides ago, I told you that event horizon will appear to us to be 100 microarcseconds wide. So what they're seeing here is obviously not the event horizon of the black hole itself. What they're probably seeing is a pocket of ionized gas to one side of the black hole. And so that pocket of ionized gas could either exist in the accretion disk, or it could exist in a jet that's coming out of the black hole. So this model that I'm showing here, and again, this isn't the image, this is just a model that they fit to the data, but this image shows the accretion disk option, where we're looking at this black hole close to edge-on, not quite, and we're seeing an accretion disk that is feeding the black hole. And the reason that it's dimmer on this side is that these photons are actually being bent around the black hole out of our line of sight as the gas is rotating around the black hole. On this side, the photons are being bent into our line of sight. And so we end up seeing a hot spot in the disk that's much brighter here than it is over here. So this is the best fit model to their data. So they think that this is probably what they're making out with this 27 to 53 microarc second radio source. The other things they're able to get from this observation is they're able to tell from the size of the source that they're looking at, they're able to tell that the black hole in the center of our galaxy is not spinning very fast compared to some other black holes that we've looked at. And those other black holes tend to be feeding a lot on gas. So it could be that ours simply isn't spinning very fast because it hasn't been accreting a lot of gas. And then finally, they can also tell from their data that we're probably seeing, assuming that we're looking at an accretion disk and not a jet, then we're probably seeing this black hole close to edge-on, but not quite. So let's talk about the future, both the future of the Milky Way's black hole and the future of black holes in general, and what their ultimate fate is. So this is the view that humans, assuming we're still around, will see from Earth 3.75 billion years from now. It turns out that the Milky Way is hurtling straight for a head-on collision with the Andromeda galaxy. And so a couple billion years from now, we're not just going to see the Milky Way, we're going to see the Andromeda galaxy about the same size in our night sky. And fortunately for us, stars and galaxies are actually so far apart, and space is actually much emptier than we often think it is, that individual stars will not collide when these two galaxies collide. So what will more likely happen is we're going to get thrown into a random orbit around the galaxy's center, but we won't actually hit another star. So assuming humans are still around and surviving at that point, the collision of the galaxies won't affect us much, but it will affect our view of the universe and what we think about it. So let's fast forward to 4 billion years. Now we're seeing this view in the night sky. And this view is, although the stars aren't colliding, the gas of the two galaxies is colliding, and so you end up getting these pockets of star formation that are going to light up our night sky. And of course, you're also going to be seeing the two galaxies tearing each other apart. Until finally, star formation will cease, and what will happen instead is that gas is flowing into the black holes at the centers of both galaxies, and you end up getting these bright orbs in our night sky, and they're going to completely dominate our night sky, making it look completely different from what we look at now. And we're going to basically be able to watch, perhaps not a quasar, but at least an active galactic nucleus in action, watching these two black holes feed voraciously on gas. And so this simulation shows, again, what this collision process is going to look like. And especially at the end, it's going to show you the ultimate fate of the two black holes. The simulation is actually just stars. It's not showing gas. But so each of these particles is a star, and as you can see, they all interact with one another and get thrown into random orbits around the center of the galaxies. And so ultimately what that means is that we're no longer going to be a spiral galaxy. These two galaxies are going to collide and ultimately create an elliptical galaxy, where rather than having all the stars in a disk, they're going to be all rotating random orbits around the center of the galaxy. And there at the end, you saw the two black holes colliding at the center. And so this collision process is actually really interesting, this idea of what happens when one black hole approaches another. So the basic physics of what happens is that I showed you earlier that embedding diagram that shows one black hole as this very extremely heavy bowling ball in a trampoline. Well, if you take that black hole and you start moving it around, you start creating ripples in space-time. And these are ripples we can actually hear. That is the sound of two black holes colliding. So those are actually the gravitational waves that we're listening to. And what we're hearing is basically you can think of it as the black holes as being paddles in the water. And as they're rotating around each other, they create these ripples in space-time. And we're actually able to potentially detect these ripples. We haven't yet. There are detectors that have been built that haven't detected anything yet. But really, it's probably more of an issue of technology and getting rid of all of the other noise that affects these measurements versus the actual idea of gravitational waves existing. But so as these black holes approach each other, they're spiraling around and they're emitting these gravitational waves. And those gravitational waves carry away energy. And so as they're emitting those gravitational waves, they get closer together and spin faster. So that's why the sound clip that I played, you hear that frequency going up. That final chirp at the end there, that was the two black holes actually coalescing into one. And that final stage is actually not very well understood at all. At least the in-spiral process is pretty well understood at this point. So that's the ultimate fate of the Milky Way, central black hole, is it's going to collide with Andromeda and will have a much more massive black hole at the center of our galaxy. But what about the ultimate fate of black holes? What's going to happen to them at the end of the universe? Will black holes just keep existing and contain all the mass in them forever? Or will they eventually, will something actually happen to them? And so Stephen Hawking in the 1970s came up with an idea that said, no, actually black holes won't exist forever. At some point, they're going to radiate away. And basically what he's saying is the black holes aren't really black. They actually have just a tiny amount of radiation. And so the way that he came to this idea is he took theories that govern the world of the very small, which is quantum mechanics, and he did a partial marriage between that and general relativity, which governs gravity in the world that we're used to. And so by doing a partial marriage between the two, he was able to come up with this idea that black holes radiate. And the way this works is he started with quantum mechanics. And quantum mechanics tells us that a vacuum is not actually completely empty space. So if you watch a region of a vacuum and you watch it over a long time, that vacuum is going to appear empty to you. But if you watch it over very short periods of time, then you can actually look into the vacuum and see virtual particles popping into and out of existence. Now, if this is happening near a black hole, these two particles are going to pop into existence in a very strong gravitational field. And it turns out this black hole can actually lend its gravitational energy to these two particles, again, exerting that tidal pull that pulled Timmy apart. Except in this case, this particle falls into the black hole. This particle isn't being pulled quite as hard, and it manages to escape. Because it's the black hole's gravitational field that has imparted energy to these particles, this escaping particle is actually taking some of the gravitational energy with it as it leaves. And since Einstein says energy is equivalent to mass, that means the black hole is essentially losing mass and radiating it away. Now, this happens on extremely, extremely long timescales for any black hole that we know about. For a stellar mass black hole, it only takes, 10 to the 67 years to evaporate completely. And when you consider that the age of the universe is 10 to the 10 years, 10 to the 67, I don't know about you guys, but for me, that, for all intents and purposes, is infinity. This stellar mass black hole is going to be around forever. For supermassive black holes, the problem's even worse. The timescale goes in proportion to the cube of the black hole mass. So if you have a million or billion solar mass black hole, it's obviously going to take even longer than that. However, it's possible that in the Big Bang, primordial black holes were created. And these primordial black holes could actually be quite small, and we could actually watch them evaporate on timescales of the universe. And the Fermi Gamma Ray Telescope has actually been looking for the signature according to what Stephen Hawking calculated. And so far, Fermi hasn't found anything. But what that says about Hawking radiation isn't quite clear. It could be that Hawking radiation doesn't exist, or it could just be that the Big Bang actually never produced those primordial black holes. And at this point, I believe the theory is going more towards the Big Bang didn't produce the primordial black holes and not so much about Hawking radiation. They've actually poked at Hawking radiation quite a bit, trying to figure out whether this is really true. And so far, it's held up to at least mathematical tests. But the problem with Hawking radiation is it produces what's known as the firewall paradox. And this is a kind of a complicated topic to talk about, so I'm going to give you a brief overview, but it's because it's involving quantum mechanics, and it's definitely outside my area of expertise, I'll just give that as a disclaimer. It's a very strange topic. But so basically, before Hawking radiation existed, you could throw anything into a black hole, whether it be particles, ionized gas, the kitchen sink, anything could go into a black hole. And ultimately, like I said with Tim the astronaut, that mass and all the information about the mass would be converted into the gravitational energy of the black hole. So basically what that means is it kind of implies that the information is lost. So all of that information about those particles or whatever you're sending in there is lost in the black hole. And quantum mechanics tells us that we cannot destroy energy. So before Hawking radiation came about, that was okay because all the information was still in the black hole somewhere, so maybe it wasn't destroyed. But when Hawking came up with his explanation of how black holes evaporate, it started to seem like, well, perhaps information could be destroyed because we're seeing black holes evaporate by emitting these virtual particles that become real. These particles were never inside the black hole to begin with, so they've always been outside, so they can't take information with them. So there are conditions you can set on Hawking radiation so that you preserve the quantum mechanical tenet that you're not destroying information. Quantum entanglement just means that the two particles basically share information. So the particle entangles not just with the other virtual particle that's part of the pair, but also with all of the other particles that have gone into the black hole before. And that breaks a fundamental tenet of quantum mechanics. It's called entanglement monogamy. So you're only supposed to be able to entangle with one other particle. To get Hawking radiation to work without breaking the don't destroy information, you have to break the entanglement. So some physicists approached this problem, and in 2012, they published a highly controversial paper where they said, well, okay, we can fix all of the quantum mechanical problems, but what that does is it creates a firewall, basically an intense sheet of energetic particles that completely engulfs the event horizon of the black hole. So now, when you send our astronaut Tim into the black hole, he doesn't make it all the way to the singularity, and he certainly doesn't pass by the event horizon without noticing. He actually gets incinerated in this firewall the moment that he passes into the black hole. So that actually breaks the fundamental tenet of general relativity, which says that you should be able to pass this event horizon because it's the principle of equivalence, which tells you that any point in space far enough away from the black hole, your experience should be the same. So you shouldn't see the event horizon as this special boundary, and you should be able to pass it without noticing. So either way, if Hawking radiation exists, then either it's breaking quantum mechanics or it's breaking general relativity. And so this has been dubbed the firewall paradox. It was introduced in 2012. And believe me when I tell you, it's definitely very far from solved. The physicists are continuing to argue about ways to get around this. And Stephen Hawking himself actually came up with an idea. As far as I know, it still actually hasn't passed peer review yet. So this is an actively discussed topic of conversation in terms of how we can get these two theories to align with one another. And I think a big part of the problem is that Hawking radiation is really only a partial marriage between quantum mechanics and general relativity. I think by approaching this problem, physicists actually have a nut to chew on now so that they can finally crack this problem of how to marry these two theories into a grand unified theory that actually tells us about everything that's going on in the universe. So I'm going to end the talk there, but obviously things have come a long way since we even came up with the idea of black holes as this kind of impossible mathematical concept. We've come to actually observe black holes. We can see black holes feed. We can watch them grow. We might even be able to, in the very near future, image a silhouette of a black hole. And perhaps most importantly, we can actually use black holes as tools to understand the fundamental nature of the universe. So these mysterious objects that we can't even look inside of, it's really kind of amazing what we can learn about the universe by studying these. So I will leave you with that.